Hi, welcome to another edition of Lo-Fi Effects Prototyping to Chill/Relax to. It's been a while. What can I say? I've had a lot going on in my life, and also, as it pertains to this work, I got a bit lost in the sauce. To very briefly summarize, I implemented or tried to implement a band-limited impulse train that was described in this Karma paper by Signalsmith. I thought it sounded pretty cool, but then I started poking around and I found that something was terribly wrong. Here's the downsampling effect that I crafted using that band-limited impulse train at a host sample rate of 4 to 4.1 kilohertz. There it is at 48 kilohertz. It's not supposed to sound like that. So I couldn't figure out what was wrong with it. And at the same time, comparing it with this other working algorithm from the synthesis toolkit that also references this paper. It was super different, but it yielded a result that wasn't totally messed up. So I spent way too much time trying to figure out how I could directly implement this algorithm from the paper, partially because of wanting to educate myself and wanting to learn how to do such a thing, but also I think a lot of ego as well, trying to prove that I am smart enough to figure this out. And I've got to say I'm smart enough to figure a few things out. One thing I'm smart enough to do is to ask for help. I'm going to give a huge shout out to Signalsmith Audio, who are a small company based in the UK focused on audio DSP algorithmic design with a mix of in-house projects, collaborations, and consulting. I'll have linked to their site in the notes. This site is great. There's a lot of great blogs that talk about audio effects, design, and implementation. There's actually one that I'd like to do sometime. I don't know if I'll do it on stream. One that I'm interested in is this Warmer Wave Shapers blog post. Really amazing. So I've been talking their ear off on Discord, and without their help, advice, I wouldn't have even gotten half as far as I got in understanding what was going on and what I'd possibly done wrong. So I figured out I can figure out one or two things, right? I can figure out how to ask for help, and I can also figure out when I need to use slightly different tools. One thing that's been really helpful to me, and I guess interesting given the point of this stream and the point of this exploration, is I went back to Python. I didn't really want to use Python. I wanted to use C major because I wanted to get instant satisfaction. Basically, I wanted to hear things as they emerged and be able to tune things. The issue was, since I was having very basic problems with verifying the correctness of what I was trying to implement, I was at a bit of a dead end. So what I did while I was asking for help was went back to Python, and I re-implemented the oscillator described in the Stilson and Smith paper. And I plotted it. Plotted the output. And as you can see, that's really messed up. It's not supposed to look that way. This was probably why things just were absolutely messed up in terms of the output. Now, what do we expect to see here? Something like this. This is the output of the synthesis toolkit oscillator. it does look a lot different, but fundamentally, as you can see, we start from zero at the 0 point, and it goes up to 2 pi smoothly, right? It doesn't do this thing where at 2 pi, it just juts up. We went through a lot of iterations of the conversation of me trying to communicate about like what the problem was, myself and Signalsmith, and we ended up kind of netting out on just use the SDK one. But one thing that I was told was, hey, remember, you're supposed to actually, when you're using this kind of algorithm, and I actually don't remember the reasoning. I think it's because this, I'll correct it later if I need to, right? So the formula given here is used for synthesis in a manner similar to the discrete summation formulae. And they mentioned that kind of offhandedly, hey, remember, if you're doing this kind of implementation, you actually need to do phase times 2 when you actually put it into the sync function. And I later realized that not only I had to do that, I just randomly did this, kind of by mistake, also used 2 times the current phase when figuring out when to wrap, and ended up with something that looked a lot more normal, at least. It didn't look totally jacked up. And it was really interesting to me because I was like, why would this work? Like, why does changing why does iterating on a certain phase, but then giving the function twice that phase, but then also wrapping at twice that phase work? Or at least work better. We'll get at that. Here is what I came up with that I thought was pretty interesting. So I made this plot in order to visually demonstrate what is actually happening in terms of the phase of this oscillator object, right? And the phase value that's passed into the sync function. We initialize phase at 0, right? So let's talk about, so this tick gets called for every sample in the buffer that's given to this object to process, right? So we're going to iterate through every sample in the buffer, and we're going to accumulate this phase and fill the output buffer with values. So let's talk about how that phase actually moves over time. So as you can see, as I said before, phase starts at 0. At every tick, it's iterated by, or it's we add to it the phase increment, here indicated as self.rate. And then every tick, we check to see if the current phase times 2 is greater than or equal to pi. And if it is, then we subtract pi from that. So that creates this movement. So we start executing, and as we tick, we get to pi into 2, and then we subtract pi, because pi into 2, of course, is greater than or is equal to pi, or whatever. So we end up getting kicked back here, and so on and so forth. So the actual range of the phase goes between pi over 2 to negative pi over 2. Now, the way this works is, on top of that, multiply the phase going into the function by 2, right? So as this moves to pi over 2, we actually go all the way to pi. And then when we wrap, we go all the way to negative pi. So that allows us to get the correct shape of the sinc function. Because the thing is it's centered around 0, right? So if we just iterate from 0 to 2 pi, the way that we would with a more conventional trig function like a sine, right? We just end up with this part of the wave. Like, so here is exactly what I was doing before, right? I was, in my implementation, I assumed that the sinc is like a sine, right? And with something like a sine, you would go from 0 to 2 pi. And once you get to 2 pi, you go back, and that's the cycle, right? But as you can see here, this only gets you half of the wave. So of course, when I was doing this, I would get a jump. I was simply iterating wrong. Everything else about the algorithm was right-ish. First of all, this looks a little goofy, and it definitely doesn't look anything like. Of course, I mean, looks aren't everything. But let's take a listen. So let's bring up. Cool. This is how the amended implementation sounds. Cool. It sounds good. I need to, well, off screen, I did verify that not only does it sound, you know, like a downsampler, it actually does so regardless of host sample rate. I'm not going to show that right now because I didn't prepare the samples and that would mess up all my business. So I'm not going to do that. So great, job done, right? Not quite. I have some terrible, terrible news. Now it sounded pretty cool, but, and super crucial, right? So let's double check the frequency here. Oh, 3,500. So one of the things that I was struggling with in the last video was the harmonics were just wrong, completely wrong, right? Right, it was changing the sound at host sample rate, and it was just wrong, right? So at least now, right, we got harmonics at the right places. 3.5 kilohertz, 7, 10.5, awesome, perfect. However, we also have a lot of other harmonics, which we really shouldn't have given the whole point of this is alias-free digital synthesis of classic analog waveforms, or, you know, emphasis on the alias-free. So I don't know what's up. It was also suggested to me that something in this is just plain wrong and I should just use the SDK. Let's compare with the SDK. Oh yeah, I need to save. And as you can see, it does not alias. So formally, the SDK is definitely a lot better. It looks right. It doesn't alias. Well, let's see how it sounds. So this is what I implemented from the paper. And this here. Sounds a lot cleaner. Then it gets really quiet at very low sample rates, which is probably the correct behavior, actually. Guess let's see what other plugins do. Of course, I'm not sure which is the best comparison, but Signalsmith? Oh, yeah, let's do that. Oh, that sounds cool. Okay, so first of all, they cut it off at 500. That's the lowest possible. Okay, so first edit. Let's think about parameterizing this in a more useful manner. So 5 is basically inaudible for some reason. I mean, it still sounds pretty cool. Okay. Let's see how Ableton's Redux sounds. Oh, yeah. Oh, that's cool. Okay, so let's bring it back. Let's see how. Hey, this is it's not correct, but bring down like around 10K. See what Redux at 10K sounds like. Nah, there's a little bit. It's a little bit annoying, I think. So I'm not sure if that is actually going to work out. What is our oversample rate, huh? Ooh. Oh. Yeah, there's a lot of the really high aliasing that's not really what I want. So, oh, that's the blit troubleshooting. So, let's bring back. Makes it so much quieter, which is too bad. I wonder if there is a way of getting around this. Once you start doing that, So we have this. It is nice that you can really hear it does not alias very much, but it starts aliasing around what, 12. You can hear like a lot of just the air just kind of gets sucked out in a cool way. You know, maybe just add like a volume boost. Because this is the end of the train for me in terms of this algorithm. Actually, that is a note that I should bring up. And I guess it's like, I suppose, the lesson. I feel like I got a bit obsessed with doing this myself when really I could have noticed that I had an implementation that worked pretty well and moved on. And that resulted in me getting really frustrated and spending a lot of time spinning my wheels. And I did learn a lot, but it's hard to say whether or not that was worth it, right? I suppose it depends on what the intention of all of this is. For me, the intention is to educate myself, but it is also kind of to get work done and possibly make things that I can use in my plugin or in other contexts. And it's also to hopefully provide something that's interesting or entertaining or inspiring for you. So I'm still trying to navigate what that actually means. But I think what it should mean is less me trying to figure out hardcore, to me, DSP, and more using my experience as an audio engineer and a musician and my professional experience as a software developer to have fun messing around with a new language and with audio effects algorithms. So hopefully the next videos are going to be a little bit more fun. I already feel it a little bit now that I've kind of started backing away from trying to get this perfect. Anyway, thanks for sticking around, and hopefully see you next time. Goodbye.